The spatial weights problem is really a problem of identification. As I already mentioned this morning, we have interactions that run with the square of n, actually because it's symmetric. If it is symmetric, it's half of that. But we only have n observations. So this is a losing battle. We can never, even in the limit, it only gets worse because the square increases, exponentially if you wish, and the linear just keeps going. So the discrepancy gets worse and worse as your data set gets bigger. So this is something that really doesn't have a solution. The way to deal with it is get data in other dimension, the time dimension, or to impose structure. And the spatial weights matrix is the way to impose structure. So essentially what we're doing is out of these n square possible interactions, we cut a whole bunch of them out. We set them to 0. And the way we do that, we'll see tomorrow, either we do it a priori or it comes out of a spatial process. So the process models the interaction of a unit with its neighbors, and from the specific mathematical form of that process follows a spatial covariance with a particular structure. And so again, we've solved, quote unquote, the problem, because rather than specifying these n square interactions, we came up with a nice little model for a spatial process that then indirectly gave us the n square interactions that we needed. In the spatial weights matrix, we typically pre-specify the neighbors to a small number of non-zero interactions, and then we force the interaction to be the same everywhere, which really simplifies the problem to the estimation of a single parameter, and that's really all we have to do. The question is, of course, which neighbors do we specify? What do we set to 0? And what I'd like to do is just give you a quick overview from some of the more straightforward ways of doing this, using a geographical or a geometric, if you wish, notion, and then give you some brief comments about how that can be generalized to social distance and economic distance. But we won't really get into this. If you want to know the nitty-gritty about this, in the readings I've included 2 chapters of a forthcoming at some point new version of the spatial econometrics book, but at least those 2 chapters have been written, and it's probably about 80 pages about weights matrices, more than you ever want to know. But it's all there, the extensions, the social weights matrices, and so on. So let's just use a simple example of 6 polygons. And what is the neighbor structure? So we can say, well, common boundaries is a neighbor structure, but we can also think of this, as we've already said, as a graph structure, as a network structure. And now the locations are the nodes, and the existence of a common neighbor, or common boundary, I should say, are the links between the nodes. So this is the same thing as the map that we just saw. And then one further abstraction is to put this into a matrix, where now we have every observation as a row and as a column, and the elements in the weights matrix tell us whether or not there is a link in the network or a common boundary among the spatial units. So formally, these are just 3 different ways of representing the same thing, the same network structure, the same connectedness structure. If you think of the element of the weights matrix as Wij, then if Wij is 0, there are no neighbors. If Wij is non-zero, I and j are neighbors. By convention, the diagonal is 0. There are no self-neighbors. Now this is purely a convention, and in fact in some social network analysis it makes a lot more sense to have self-neighbors. In that case, the diagonals would all be 1. It doesn't really matter conceptually. It does matter when you make the derivations. And the reason that I prefer this one is that in a lot of derivations, and we will only touch on this at a more intuitive level, but a lot of derivations, we require the trace of the weights matrix. The trace of a matrix is the sum of the diagonal elements. And it's of course a lot easier when that trace is 0 than when that trace depends on the number of observations, which is the case when it is 1. So when you have 1 on the diagonal, the trace will be n, which will mess things up as we go to the limit, because the trace will go to the limit as well. But if you have it nice and 0, then it doesn't change no matter how large the data set is. It remains the same. So those are some practical reasons for keeping it to 0, but conceptually either one is fine as long as you know which one you do. Of course, in the past there has been some software that assumed it was 1 but didn't tell you, and so then unless you really dug in and did some experiments, you would come out with some really weird spatial autocorrelation coefficients. So as long as you know what you're doing and what your software is doing, you should be fine. So then, yeah.
Quick question. In the previous slide, how would you interpret the rows and columns? The rows probably suggest
This one?
The rows suggest it's a neighborhood characteristics. What is adjacent to 1, or what is the adjacent to 1, 1, 1, 1, 2, 1n? But how would you interpret the column in the matrix?
It's the same thing. I mean, most of these weights matrices are symmetric. They don't have to be. And there are directional processes that move in a particular direction, say particularly in hydrological systems, for example. You know, water flows down, it doesn't flow up. So then that gives you particular structure for the weights matrix. But the Wij is I related to j, but adjacency is a symmetric concept. Distance is a symmetric concept. So those are the same. It's when you have directional effects that you typically get triangular structures in the weight matrix that then ij and ji matter, which direction you take. So in essence, what I wanted to say is that whether you depict the connectedness by a map of spatial units and you focus on the common boundaries, or you depict it as a graph of a network with nodes and links, or you depict it as a matrix with zeros and ones, it's all the same thing. It's all referring to the same thing. Okay? And then what we will be using is this matrix format, but I just want you to know that in practice you never actually use a matrix, because if you look at this carefully, you see a lot of zeros. And it's never a good idea to carry a lot of zeros around. And especially in realistic problems, say, if you look at US counties, there are 3,100 roughly continental counties, much less than 1% of the matrix is non-zero. Just think about it for a second. What is the row of a contiguity matrix for 3,100 counties in the US? Okay? You have this county, let's say, and then you have 5 neighboring counties or 4 neighboring counties. All the other ones are 0. So most of the weights matrix is 0. And from a practical point of view, that's not a good thing to store in memory or multiply with or do anything with. So in practice, the way we actually deal with these weights matrices is to store them in sparse format, which means we only store the non-zero elements. But I will refer to them as matrices because that's how we manipulate them mathematically. And also when we go to the model specification and the estimation methods, we will use matrix algebra and properties of matrices, but in practice, we don't carry the zeros around. Okay. So then, where do these weights come from? The easiest ones are the geographic weights. Why is it easy? Because the GIS can do it for you. GIS, geographic information systems, are very good at figuring out whether point A is close to point B, or whether the boundaries, because they're all digital, of 2 polygons have common segments or common points. So that's a way you use the GIS. That doesn't mean, and it really shouldn't mean, that this is the only basis for your spatial weights matrix. They can be based on socioeconomic concepts, on social network concepts, and so on. It's perfectly general. Anytime, as I like to put it, anytime you can think of a phenomenon of consisting of elements that can be represented as nodes in a network with connections to some other nodes, not necessarily all the other nodes, then we're in business. This gives us the formal framework to use a spatial weights matrix to apply spatial regression and to carry out tests for spatial autocorrelation. Now, in those contexts, spatial is not going to mean the same thing as geographical neighbors, but it will mean connectedness in some network structure. So if you look at some of the social network literature, the formalisms are exactly the same. The equations are written the same. The interpretation, of course, is different. What I wanted to end with is just a quick illustration of the easiest way to construct spatial weights, namely contiguity weights. And contiguity is about having a common boundary of non-zero length. And as I mentioned to you, a GIS is very good at doing this, but there's also a danger in that, because a GIS is ultimately only what you put into it. And the boundary of a county is approximated by a polygon. And a polygon consists of line segments. And it really becomes a matter of choice, of discretion, to decide at what point a line segment has zero length. I mean, you can think of the boundary as continuous, and you have to approximate that by discrete line segments. And some GISs are cruder than others and would simplify things and have, a line segment is basically, say, a kilometer, or a line segment is a foot. Makes a huge difference when you let this GIS figure out whether two units have a common boundary or not. So this is one of the dangers of working and letting the GIS do the work for you, because you're really totally dependent on the level of generality or specificity, if you wish, in the GIS itself, whether something is a line segment or just a point. Also, in practice, you have to be aware of how your spatial units have been digitized, if you wish. And this is particularly relevant when you work with cities with streets. Say, if your data are census tracts, is the center line the census tract boundary, or is the built-up area the census tract boundary? So if you really want a detailed GIS, typically the streets are actually in there as separate polygons. If your analysis is for tracts, there is emptiness between the tracts because the street goes there. And so then they become islands, they become disconnected. And these are the kinds of things where the GIS throws a loop at you, because it is more precise than you need to have for your analysis. And what you need to do then is somehow generalize the GIS so that these tracts start touching each other, so that it can then accurately assess the fact that whether two census tracts have a common boundary or not. These are the kinds of gotchas that the GIS gives you. There's a couple more that are described in these chapters that I was referring to. So the GIS is very powerful in doing this work for you, but it can also give you some weird results. And we get examples of this on the open space list all the time. GeoDa doesn't give me the right weights matrix. Well, GeoDa only works with the information that goes in. If the boundary files that go in have gaps between them, then these polygons will not touch each other, so they will not be neighbors. If they have to be neighbors, the boundary lines have to match, and that is something the GIS has to do. GeoDa doesn't do that. So, knowing this, we can think of contiguity in terms of how extensive is the actual connectedness. And let me clarify this. It's whether we look at common boundaries as being a full line segment, or including the corners, or only the corners. Let me illustrate this with a regular grid pattern. So we have a regular grid, very simple, 3 by 3. We're looking at 5 in the middle. What are the neighbors of 5? That's the question. So the first way we could approach this as, say, all the units that have a common boundary. So those would be these, north, south, east, west, have a common boundary with 5. This is what we call Rook contiguity in analogy to the chess term. So in this case, we have 4 neighbors, north, south, east, and west, and they are the ones that have a common boundary. Okay. Then we could say, well, why common boundary? Why not common corner? And then we have another one. Oh, these are the weights, the Rook weights. You see lots of zeros. I won't dwell on it. If you have time, look at it. What you see is these typical band patterns. These are not, if you're familiar with sparse matrix calculations, these are not the kind that you want, because they do not stay very close to the diagonal. They kind of jump around. And especially with larger data sets, you have these kind of lines of ones. It's not easy to make this compact in the traditional way. So you really have to think about how you handle this. Bishop contiguity is the common corners. Now again, we have 4 neighbors, but they're not the same. So as long as we have stationarity, that shouldn't really matter, because, you know, however we move our window over the data, we should get pretty much the same indication of covariance. However, when we don't have stationarity, when we have directional effects and things like that, then these might give very different results. Now what happens, you know, you might wonder, well, why would I do this over the other one? And it's really problem specific. It's subject specific. You know, in some, it really depends on how the interaction works between these units. You know, you could have situations where cities are cut up in districts, and the only way you can get from one district to another, let's say they're walled districts, and there are gates at the corners of the district, and that's the only way you get in and out. That's the way the interaction works. Or if you have invisible boundaries, then you just cross the boundary and you're in the next one. So this is all dependent on the particular process. I've seen just about anything of people with different types of interactions that come up with the weirdest reasons why the weights matrix should be what it should be, and that's fine. You know, there is no best weights matrix. There is no optimal weights matrix. It's really, I'll comment on this a little bit more later, but it's really problem specific. So each of these, the rook and the bishop, give us 4 neighbors. They're not the same, but we have 4. When we throw them together, we have what we call queen contiguity. And queen is all-encompassing. It's both the corners and the common boundaries. And now we have 8 neighbors. Not 4, but 8. Queen contiguity will always have more neighbors than rook contiguity. Okay. Which is better? 2 ways to think about this. One is, and we'll do that on Thursday. One is diagnostic testing. When you do a specification test, what you want is a test with a lot of power. So you want a test that can detect slight deviations from the null hypothesis. So then you want a weights matrix that doesn't include too many neighbors. Because if you include too many neighbors, there's likely to be some correlation if you have, you know, just by averaging. So if you have very few neighbors, then you tend to have a more powerful test. So for diagnostic testing, I tend to use the tightest possible neighbor structure that I can to detect some deviation from the null hypothesis. So this is purely pragmatic. There's no theory here. This is just a rule of thumb. I've done this for a while. You know, I have a feel for it. Let's just put it that way. And this is a good way to think about it. It's a very different story when you're interested in modeling spatial interaction, because there ad hoc is no good. The model of spatial interaction, the weights matrix that you use for that, should match the kind of interaction you have in mind for your substantive model. And that's a lot trickier. That's a lot harder to do. And in those cases, whether it's rook or queen, really depends on what it is you're trying to model and actually how substantive your process, your model for spatial interaction is. You know, as we saw this morning, it could again be more of an ad hoc thing where you try to filter out the spatial autocorrelation. So then again, you want to have a weights matrix that's a good filter, so that after you've done the filtering, what you're left with is a proper random variable that is no longer spatially correlated. But if you're really interested in modeling spatial interaction, your theory should give you the structure of what the weights matrix would be. Now, this is easier said than done.
Is there a quick diagnostic for fewest neighbors? In other words, this would be SO, I guess?
No, the way you, I mean, as you'll see in the lab, there's a whole range of different weights matrices that you can construct, and you can basically move outward. So say you start with first order neighbors, then second order, there's a bigger band out. So you want to keep that tight.
I simply meant if you're trying to choose between rook, bishop, or queen, queen would get most. And for diagnostics, you're saying you want the fewest neighbors so that you're not getting this as a function of the number of neighbors. Is there some quick thing that I could do in GeoDa to determine, I mean, kind of look at the gal matrix, for example, or list and see, count the number, or is it?
Well, no, I mean, there isn't actually, but one thing you can do is look at the distribution of the number of neighbors. So when your weights matrix is based on an irregular spatial layout, not every unit will have the same number of neighbors. The closer you get to a grid structure, the closer you have these ideal situations that I just showed you. Okay, so you have city blocks that are squarish or rectangular, you will get close to the grid situation. If you have highly irregular counties, then you won't. But you can still use the same concept, as we'll see in a second. So in some states like Colorado or Kansas, and Iowa, most of the counties are rectangles. So then you get close to this situation. And then there will be a big difference between using queen or rook, because all the corners get included as well. When you have more of an irregular structure, there usually isn't that big a difference between the two. This is an illustration. So in an irregular setup, what we use the terminology for is rook when it's common boundaries, and queen when we also include the vertices. And this is an illustration, if you look at the circular area, where depending on the GIS, this corner will be a point or a tiny little segment. If it's a tiny little segment, it's counted as rook. If it's an actual point, then it's not. And the queen criterion would take them both.
Thinking about maybe something like illegal immigration by states or something like that, wouldn't the length of the boundary matter? The one of the long, irregular.
Yeah, what I've done so far is just give you some basics. These are essentially 0-1 type matrices that you can then row standardize and so on. But you can also have general matrices where you include area, length of boundary, distance between the centroids, anything that makes sense basically. And length of boundary is a common one, because you can, and it's also asymmetric, because you can have, a large country or a large state having a small fraction of its boundary with another state, but that fraction is a very large fraction of the boundary of the other state. Let's say, you have a large state with a very small thing, and then a small state that is squarish. So this would be 1/20th of the length of the perimeter of the large state, but it would be 1/4 of the perimeter of the small state. And so there are ways to put these kind of weights into the spatial weights matrix as well. But I don't want to dwell on this too much. The labs are there to work this out, and if you want to see just about as many different combinations as I could think of, then I refer you to those 2 chapters, and you'll see different ways that people have combined this in the literature to come up with the weights. one caveat, thing to watch out for is that the more structure you put in the weights, the more you're starting to model interaction. If you just keep them very simple, and that is a major point in favor of keeping them simple, then you put the model in the rest, in the regression part or in the functional specification. As you put more and more into the weights, you're moving towards this gray area where the weights themselves become a model. And that becomes highly it's not that you can't do it, but it's much more complex, it's highly nonlinear, and it's something that requires even more complex methods of estimation and testing. So typically, we like to keep the weights, as we call them, exogenous, meaning not jointly determined with the rest of the model. And that explains in part the popularity of geographic weights, because you have nothing to do with the boundaries of the counties or the census tracts. If you start using socioeconomic weights, then you get into a situation where maybe these weights are jointly determined with the rest of the model. An example is if you use racial composition of a state to compute a distance measure. And so you get the percent, say minority in each of the states, and you take a simple difference of that. That is a measure of distance between the states, economic or social distance, and then you use that as the basis for your spatial weights matrix. Now, if you're building a model of poverty, there's a high correlation between these two. Then you start getting in trouble into identifying properly what part is really inside the model and what part is inside the weights matrix. And that's always going to be a concern as we build more and more complex spatial models. The identification is a major problem. And here again, as I mentioned this morning, space-time is a lot better than pure cross-section. But in the pure cross-section, it's highly limited. We are constrained. There's not that much that we can do. So the more sophisticated you make your weights matrix, the more complicated you make the whole analysis, and maybe to the point that it's over-modeling the data. The data really have to support this kind of modeling. And I tend to favor very simple spatial weights matrices and to put more of the complexity into the model itself. But it depends. If you're trying to model complex spatial interaction, there is a strong argument to make your spatial weights complex, if the data support it.
This is a question about row standardization. So one of the things you do is row standardize, wider than the neighbor.
Yeah.
How does that, it obviously doesn't affect, how does that affect the computation of Moran's I? And is there a way to reflect that in the formulation?
It's in the formulation. The double sum over Wij and the cross product divided by S0. S0 is the sum of all the elements. So you can think of S0 as the sum of the row sums. Right? So if the rows, there's a lot of row in here, are row standardized, right? Their row sum is 1. And the sum of the row sums is n. And that n cancels out with the n that we have in the denominator. So that's a simplification. And we'll use that a lot later on when we use matrix notation. It's basically z prime wz over z prime z. There's no n's or s0s anymore. It's gone. But in terms of the interpretation, there is really no difference. It's whatever is in the weights gets sorted out, and I didn't give you the technical detail, but when you compute the mean and the variance for Moran's I, say, under the null, then these weights are very prominent in there. And depending on what you stick in those weights, the results will be different. So whether you row standardize or not, it will give you a different mean for the Moran's I and definitely a different variance. The mean actually doesn't matter, but the variance will be different, and that will affect the z-values that you get. So for the same data, the same spatial layout, you can have a different result whether you use a non-standardized or a standardized weight matrix.